Morning to all. Today we have one very important topic related with sustainable, clean and green energy solution with reduced carbon footprint for grid integrated hybrid system. It is very important because as we are moving forward towards the Viksit Bharat in 2047 and expecting a $30 billion economy of the country, we need that this clean and green energy solution should be there, because with the help of this petrol and diesel we cannot expect this much. We have with us Professor Dr. Abhinav Saxena, who is from the Department of Electrical Engineering, JC Bose University of Science and Technology, YMCA, Faridabad. Thank you very much, sir, for accepting our request and delivering a talk on this very important topic. Certainly, it will give us a direction where to move and how to move. We have Dr. Abhinav Saxena belongs to Bareilly, Uttar Pradesh. He is BTech from UPTU Lucknow and MTech from IIT Roorkee. He did PhD in electrical engineering from Jamia Millia Islamia. His research areas include renewable energy-based power electronics and derived electrical mechanics, machines, power system, artificial intelligence techniques, machine learning, design of non-linear controller, smart grid, electric vehicle controlling, including battery charging, congestion management, DG, energy management, artificial intelligence technique, analysis of biological equipment, machine learning, sustainable and green solution. He is having a teaching and research experience of more than 12 years. He has published more than 100 research papers in various SCI scopes, Web of Science journals, book chapters, and in various reputed conferences like IEEE and Springer. He has also published 18 patents and 4 patents have been granted. He has completed the research grant of rupees 5 lakh under the scheme of AKTU, Vishweswara Research Promotion Scheme. Recently, he has also received the Best Teacher Award 2021. Congratulations, sir, from Dr. APJ Kalam Technical University, Lucknow, and Excellent Teacher Award 2022 from AI Falah Community Council. He has supervised one PhD student and co-supervising 3 PhD students across the various universities of the nation. He has delivered many lectures as a keynote speaker in various conferences and FDP. He is also a senior member of IEEE. Currently, at present, he is working as assistant professor in Department of Electrical Engineering at YMCA Faridabad. Thank you very much, sir. Thank you very much for accepting this request. We have with us our Honorable Shri B.N. Dixit, our Director Legal Methodology. Sir, thank you very much for always with us on this platform and to motivate us how to do better in the legal methodology or in science and technology in our country. The standard of the country need to be uplifted in all sectors of life. This is the most important thing because India is now not developing. We have reached at a level where we can say now we are very near to be developed. So, sir, I would like to request you to kindly speak 2 words. Thank you very much, sir. Over to you.
Okay, thank you, Astosh Ji, Director Legal Metrology, Government of India, for nice word you had given for me as well as for Dr. Saxena. And on the topic also, the green energy is very important topics. It is not only the electrification of the vehicles and all those very things. There is need of the uh, f- uh, lot of trees are being cut in Delhi due to construction of new building, for the widening of the road, or for various reason, for the construction of the building and all those very things. So that is also playing very important role because the greeneries are being down and down. So there is need that only the electric vehicle and green energy revolution and all those type of things. So the government had taken decision, lot of decisions that this type of electrical vehicles will be on the roads, and lot of promotion has been given. So many charging stations has been developed. Even IOCL, PCL, they are also making the charging on their very stations there. So lot of places are being placed where the this electric charging system has been done there. So government has given motivations, means they are giving concession for the purchase of the vehicles and so many other type of things that people should go for this uh, electrical vehicle, and less pollution should be on the roads and all that very things. The Supreme Court also has been taken um, uh, acknowledgement that there is lot of pollution in the country and there is need of the green revolutions and so many type of things is there. So now these days only the imported vehicles are there, that is the green vehicles are there. It means that electrical vehicles are there. So there is need that this should be constructed in India also to promote the business so that the common peoples may reach to those very things. And now the the vehicle which is coming in the market, these are the not less than 65 lakh rupees. So apart from that, very cost and all those type of things are there. In the other countries, you will find that whenever these electrical vehicles are there, on the roads are there, on the roads, these facilities has been made that this will be automatically recharged. Suppose at the red light, the vehicles are there. So the things has been made that the whatever the vehicles will be there, that will be automatically recharged. So in that way that the mileage will be increased and people will be encouraged that their vehicles may run for a longer period, and they should be not worried that this will be discharged very soon and wherever they will go. So now the battery charging system is very important, and the vehicles are going up to 80 kilometers and 100 kilometers. So that is playing very important role that throughout the day the people can do their business. Earlier it was not. So this is very big change in the system, that 80 to 100 kilometers driving facility in the battery is there. So day by day, the government will take decision that how to improve all those type of things, and more number of the peoples are going for the electrical vehicles. So you'll find that in coming 5 years, Delhi will be flooded with the more number of the electrical vehicles, and government will be benefited and people will be also benefited, and there will be less pollution and all those type of things. So Dr. Ashutosh Agrawal has taken very good initiative today that to start this type of program which is related with the common peoples, and due to this pollutions, lot of peoples are dying in Delhi. Their lungs has been affected. Lot of queues are in hospital, and I have seen that whatever the queues and uh, problems are there in the hospitals and everywhere, their lungs has been affected. Even the common children of the less uh, of the 10 and 20 years age, they are also been affected. So this type of initiative is very good, that even if it is followed in the bus and the school bus and all those type of things, so it will change the whole scenario of the country and the people will be more benefited. The rest is on the Dr. Saxena, how he will give the emphasis that how these systems will come and what is the advantage, disadvantage, and how it will be implemented. That is very important roles. So we are in support of this very technology, and we are always standing with the government and Dr. Ashutosh Agrawal, and we will encourage people and industries in the seminars. Thank you with these very words. I hope that today program will be very successful.
Thank you, sir. Thank you very much for your kind and motivating words. Thanks a lot. Thank you very much. Now, I think I would like to request our Professor Dr. Saxena to kindly deliver the talk. Over to you, sir. Sir, after this program, I will share this PPT as well as video in the social media platforms as well as on our government portal, where any participant can download and see at any point of time with your kind permission.
Okay. So before I start this presentation, just please confirm me whether I'm audible to you or not
Yes, very
properly.
well, very well, very well.
So, can you see this change in slides?
Yes,
Let me check
yes,
on this
yes.
one.
Yes, sir. It is the first slide only right now.
Okay, that's fine. Yes, I want to see here. Now is it okay, sir?
Yes,
Can you?
very well, sir. Please continue.
Okay, fine, sir. Okay. So before I start this presentation, I am highly thankful to Dr. Ashutosh sir, Director Meteorology, for inviting me to share my experience and knowledge related to this topic on such a very good portfolio. So I am highly thankful to you, sir. And the special thanks to Professor B.N. Dixit, sir, for giving us a motivation words related to this sustainable, clean, and green solutions. And sir has also given emphasizes about the need and the challenges we face. So I'm also going to discuss the similar kind of things in this talk here. So before I start this talk, you can see like the topic is the strategic for sustainable clean and green energy solutions with reduced carbon footprint for a grid integrated hybrid solutions here. So basically, this talk is all about reduction of carbon footprint in conventional uh, power generating sources here. That is a thermal power plant. And in addition to that, we'll also see how it can provide you this green solutions here. In addition to that, we will also see like the grid integration of renewable energy sources, especially to wind and solar, how they contribute to provide this sustainable and clean energy solution, because we know that they are totally zero, they provide zero carbon footprint here. So, but still there are certain challenges with that, because this topic is for green and clean energy solution. It is not a national concern, it is a global concern. So if you see like from the past few years, any global summit, uh, uh, any global summit which was took place, they directly or indirectly discuss the need of clean and green energy solution. Likewise, if we see in the last year, that is 2023, Global 20 Summit has been submitted in India, where the global leaders across the various countries has come to our country and they discuss about it. So the theme and motto of that global summit was like a Vasudev Kutumbakam. It means it's like one earth, one family, and one future. It means uh, an earth only can survive when we have a ambient number of families. And the family can survive when they have a good future. Okay. Future means it can be long and sustainable solution. If you see in this current scenario, the sustainability is one of the biggest concern there, because as you can see in the surrounding, especially the NCR and nearby areas and its neighboring areas, there are a lot of pollutions here. We have a lot of carbon dioxide, nitrous oxide types of toxic gases are available, which directly create the pollutions and increases the AQI level here. Okay, so as of now, you can see like the AQI index touches, especially in the NCR region, above 500, which is highly dangerous. Okay, so at 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 this point of time, it is very difficult to sustain even for the small kids here. Governments are a lot of are doing a lot of planning to work on this part here, but still there is a lot of scope of improvement is required. So my strategy is somehow how, because this is simply a one part of this carbon footprint, because there are a lot of as Ashutosh had discussed about, like there are a lot of sources like our conventional vehicles here, like trucks and car and all everything. They are continuously producing a smoke, and the various industries like this leather industry, they are also producing a lot of smokes here. So they're directly, indirectly, they're providing a lot of carbon here, which at the end affect the pollution set. This is simply a one segment of reducing this carbon footprint here, because we are totally in this talk. We are totally dealing like, especially in the conventional thermal power plant, how I can reduce this carbon footprint here. So it is simply like a pure mathematical analogy and optimization techniques has been work on
I'm
it.
sorry, sir.
Which
I'm sorry, sir. Slides are not moving. It is on the first slide only.
yeah, sir, I am not moving. It is
Okay.
I'm
Thank you.
on the first slide now.
Thank you very
Okay,
much.
sir.
Thank you. Thank you.
Okay, fine, fine. So let's see what are the various challenges. So can you see this next slide?
Yes,
Ashutosh
sir.
sir, please
Yes,
confirm.
sir. Yes,
Okay,
yes,
fine.
sir.
So okay, fine. Thanks, sir. So as we see, what are the challenges with our conventional energy source, especially if we talk about the thermal power plant? So conventional energy sources like mainly coal, means it is like a thermal power plant, while natural gas and our hydropower plant. They were they were facing the several challenges like, especially in terms of technical, environmental, economic, and social challenges. But if in detail we see the challenges like environmental challenges, resources depletions, economic challenges, efficiencies and technical issues here, health and safety concerns, waste management problems, social and regulatory issues, sustainable and climate commitment. So let's see all these challenges here one by one. To begin with the challenges number one, the first we see the environmental challenges. This is the biggest and the major challenges with the conventional generating units here. As we all know that from the last 2 decades, the level of global warming is continuously increasing. So the major contributors are the greenhouse gases. If we see the greenhouse gases you talk about, it is basically like a carbon monoxide, nitrous oxide, and all the particulate materials, SO2. They contribute, they directly affected the not our this environmental, but also affect our health. At the end, it sometimes this also cause the acid rain here. But it's a very that is a very rarest issue here. Okay, so but if you see this contaminated and polluted gases here, these are at the end affect our global warming, and they also allow the climate change. Climate change, if you see from the last 1 decade, the summers are increasing and winters are getting short. That is because of this global warming here. If something is happening, and we're also expecting in the upcoming years, the summers will cover almost 90% and winters will cover the 10% of the whole year. That is one of the alarming situations if something is happening like this, because because that directly affects this health issue, and the major concern is it also affects our agriculture sector. Okay, so the agriculture, because as we know that the agriculture sector in India is directly is a seasonal dependent. Okay, if the seasonals have a lot of variations, it means the agriculture production will definitely get affected. If the agriculture sector get affected, it means the economy and the cost will also affected. The cost of these vegetables and other products will also be increases. At the end, we can say the inflation will increases here. Okay, so so this is like uh, so it is required how we can work on to reduce this carbon footprint, and which is contributed by this air pollution gases like greenhouse gases and all. Another thing, the for the environmental challenges is the water pollutions. We know that the discharge of all the unwanted material, the conventional generating units, they to the river here, which at the end contaminate the water with this all this unwanted material, and at the end it causes the water pollutions here. So this is also a very typical challenges here. And the next thing is like the degradation of land, which is due to mining and fuel extraction. Because day by day, the mining process and this fuel extraction is also increasing here, which at the end degrade our land. So, which is also the biggest concern. So, these are the environmental challenges on which we have to work around. Because if we cannot work all these environmental challenges, the survival, our survival will be quite difficult, especially in terms of everything. Another challenge is called the resource depletion here. So if you see the resource depletion, like the finite nature of fossil fuels, especially the overall the reserves, they are starts decreasing steadily. The another thing issue is that the enhancement in the difficulty and the cost of extracting the remaining resources. If you something is like to our natural resources, they are continuously degrading, and the extraction is also very difficult. If the extraction is difficult, it means our ways, the topologies and methods which we are having right now for extracting the available resources, they are also become very costly. It will become very quite difficult to avail such type of thing here. Further, now our reliability on the imports on fuel security, especially for oil and gas. So likewise, if you see more in India, like they are extracting the sources from the countries like Iran, Russia, and all, especially like gases and oil. So our dependency on all these country, our dependency on all this fuel security will also increase. It means we have to give a more importance, import tax, okay, rather than the this export tax which has to be provided here. So such dependency has to be reduced. Another challenge is the economic challenge. If you see as a, if you consider the challenges one and two, our rising fuel costs and the price volatility in the global market. It means directly talking about the inflation. Okay, inflation increases. It means our economy and GDP is also get affected here. It means the enhancement in the fuel cost and the price volatility will also be affected here. Further, the maintenance cost and the operation cost over the lifetime is also increases because at the end, if this concerns of the this conventional generating units, we see there are two type of costs: running costs and operation costs here. Okay, more or less, if we talk about the thermal power plants, so they are having a more initial cost, but some lesser or optimal operation cost. But if such type of things are happening here, and you can see, like in that case, this operation and cost and maintenance cost will also increase. Further, our environmental compliances like carbon taxes and emission control, if we have more amount of carbon emission, it means the particular industry has and the individuals can also have to pay the more carbon taxes and more emission control. Further, if you see the long construction duration and high capital investment, the same thing here. The next challenge is like the efficiency and technical issue. Okay, so if you see like the carbon emission is basically kind of losses here. Okay, it means whatever the we given the input as an in the form of steam. So you find out that if you have more carbon losses, it means that totally are more thermal losses. Okay, more thermal losses means will having a layer lesser efficiency. Lesser efficiency is directly concerned that we have a lesser uh, output here. Okay, so lesser efficiency means lesser output, or we can say like it would also allow the increase the cost of the system that we have already discussed here. At the end, the aging or this traditional infrastructure, which also having a reliability and maintenance problem here. These are the few issues with this thermal and conventional generating units here. Further, if you see the limited flexibility and respond to rapid load changes, because we know that year by year the load is increasing here. So the thermal power plant has to respond to the sudden change in the load here. Okay, so this should have a more flexibility, but as of now, if you see, they have a limited flexibility. Okay, next is like the health and safety concerns. If you see, they have more occupation hazards in mining and fuel handling. People are also getting affected. Those who are working near the mining, they are very difficult for them to get sustained. But at the end, they are on the verge of the accident. They have a lot of risk of accident here, especially like coal mining disasters, oil spills, and everywhere. Because sometimes the workers who are employed near the mining, they have to measure the reading, they have to work on it. Like They have to carry something, materials and all. So that is why highly challenging here. The another part of this conventional unit is the waste management problem. It means the disposal of coal ash, sludge, other solid waste materials. Law and and another thing is they are having a more long-term environmental impact here for waste storage. So these are the few concerns. Another is like the social and regulatory issues. The government has also uh, they also produces certain guidelines for the installation of this conventional generating units. So they are simply like to so that public opposition due to the environmental and displacement concern can be also considered here. At the end, the last is the rehabilitations and resettlement issue, the large mining projects here. Because at the end, hota kya hai कि sometimes we see whenever a plant has to be stored or set up because they need a more space. Especially if we talk about the hydropower plant, they are supposed to install in the hilly areas. So it is very difficult to settle the local people who are nearby, who are living nearby to that plant. So it is required to resettlement. There are certain land issue and as per the regulatory norms, so that they can offer their lands so for the and help the government for the installation of this hydropower plant. And the last and the most typical challenge is on which our talk is talking about the incompatibility carbon with zero emission target. It is talk about the net zero carbon emission, which is not possible with the thermal power plant and the hydropower plant here. Especially we talk about the thermal power plant here. And then I told you that through the ash, we have some unwanted material that had been discharged in the form of smoke here. So we want to have a lesser carbon footprint and the net zero carbon emission, which is very difficult to obtain. So we have, in this research work, we have produced something, our algorithms, few mathematical computation process that will help and that has been assessed to help this zero carbon emission targets here. Because at the end, if we have a zero carbon emission targets, it can produce the reduced long-term viability compared to the renewable resources. What does it mean? It means if we can expect a zero carbon emission targets, it means like that is only be possible if we can work on this long term viability project. If we compare with this whole concept with the renewable energy sources, because we know that in the renewable energy sources they are directly providing the zero carbon emissions because they have no concept of this carbon footprint and all. But the viability cannot be considered, especially for long term viability, because if we talk about a solar power plant, they have a totally life of around 20 solar panel. If we see like they have a life of 15 years to 20 years here. So after that, they are required so much of maintenance and cost. But at the end, this thing can be compensated at the cost of the zero carbon emissions here. Okay. So in this study, we will see how we can minimize our conventional energy sources here. How we can minimize this reduced carbon emissions. So in my research work, if you see, Ashutosh sir, am I audible properly?
Yes, sir. Very well. Very well. Please continue.
Okay. Okay. Thank you. Thank you. So in my research work, if you see, there are three aspects has been considered. The first, the topic is like a grid hybrid energy integrated system. So in the hybrid integrated system, I've considered the few renewable energy sources and our conventional sources here. So as I considered like the wind energy sources, solar photovoltaic sources, thermal energy means our conventional sources here, battery energy storage systems, with the purpose of providing the eco-friendly, economic viable, sustainable and reliable solutions here. Because this sustainability and reliability can only be assessed if we can integrate the renewable energy sources with our existing conventional sources here. So the objective of doing this is mentioned is like it has to reduce the carbon capture. There are three things. Generally, the common language is called carbon emission. But carbon emission has been described and considered in terms of three aspects. The first is called carbon capture, carbon utilization, carbon footprint. Okay. So if we see carbon footprint is basically a difference between the carbon capture and carbon utilizations. And mathematically, the carbon emission has been expressed in terms of loss of carbon emission, that is LCE. Okay. At the end, this is the one aspect. Third aspect is, as I told you that we have considered the variance component. So we want to measure this and we want to reduce the cost of all the individual components here. Okay. So to measure the optimal size of various components and distortion level. Distortion level means harmonics content because when we have an integrated system here, so directly, so we can say like that the integrated system is having a lot of disturbances and the disturbances has been turned out in terms of the harmonics here. That also we checked. Okay. And after that, we have checked the optimal cost in terms of loss of cost of energy for the various loss of power supply. That we'll see here. So our objective of this research, first we have developed our multi-objective functions. And that multi-objective function is basically developed in terms of various components, like in terms of like carbon footprint, carbon emissions, carbon utilizations, loss of carbon emissions, and the individual component size of the integrated systems here. So at the end, we have to also optimize the various components here. And further, this objective function has been trained by this the hybrid machine learning algorithm here. It is simply like the hybrid heuristic, hybrid hysteresis fuzzy logic controller. So this basically controller is basically the combination of fuzzy logic as well as hysteresis. So once this is algorithm has been applied on the objective functions, so it is expected to have the optimal cost of the system, reduce carbon footprint, minimal harmonics, and that can be assessed by maintaining the proper balance between carbon footprint and carbon utilization. At the end, we also observed like the average value of these methods are found to be like 0.529 per kilowatt hour and this 70.64 gram and everything. This we'll discuss at the end here. So these are the objective of my research here. So all over this integrated system has been worked on this IEEE 9-bus system. So this is basically IEEE standard 9-bus system here. So in this one, basically you can see we have the 9 buses, and out of these 9 buses, we have the 3 generating units that are connected at the bus number 1, 2, and 3, and we have these 3 nodes that are connected at bus number 4, bus number 5, and bus number 8 here. This is standard one, and accordingly, because as I told you that we also have to place in the standard IEEE bus system, we have only conventional generating unit. We don't have a renewable energy generating unit. Okay, that is that like solar and wind. So we have to place these solar and wind energy units on this IEEE bus system. So for that, we perform a load flow analysis, and after doing the load flow analysis with a very known method, is called Gauss-Seidel method. We got the real power losses between the 2 buses. Like in the tabular form, you can see between bus 1, 2, we have the real power loss 0.36 and 0.41, and subsequently and on. So after having the real power losses between the 2 buses, thus our requirement is to place the renewable energy, especially solar and photovoltaic, at that bus where the losses are minimized. Okay, so because this real power losses, the minimum real power loss is being considered here, because so that the more load requirement can be met. So as here you can see, bus 4 and bus 5 has been considered for the placing of this renewable energy sources here. So this is again our structure of proposed model. As I told you that bus number 5 has been selected for the placing of solar photovoltaic and wind turbine here. So as here you can see, we have taken nonlinear routes. And in this proposed one model, you can see we have a wind turbine here, which is converting our mechanical energy to electrical energy. And the output of this goes to our bus number 5 here. And the voltage level has been adjusted to this transformer. Further, we have AC source here. That AC source is basically like a conventional sources here that provides the power here. Another renewable energy sources we have the solar photovoltaic array. Okay, so we know that the output of solar photovoltaic array is DC, but our bus number 5 is AC here. So what we'll do, we'll simply connect an inverter between the uh, output of solar photovoltaic and the bus number 5. And the tuning of this inverter has been done with the help of hysteresis fuzzy logic controller here. Because at the end, this inverter is a part of this controller devices here. So until unless we provide the proper gate pulses to the inverter, this inverter will not be conducted. So the gate pulses to the inverter has been provided with the help of the hysteresis fuzzy logic controller here. Another thing, if you see the BESS, that is called battery energy storage system. So here you can see the battery has been the storage stored the power, and the stored power of the battery has been transformed into AC with the help of an inverter. Again, the same thing, the switching of the inverter has been done with the help of the hysteresis logic controller here. So this is our structure of proposed model here. So let's discuss all the sources one here one by one. So first sources, we have the wind energy source. You can see like the wind energy source is connected to the bus number 5 here. So because this all the renewable energy sources, especially wind and solar, because they have a continuous variable output. So if we talk about the wind we have a variable wind. Accordingly, we have a different power at the different wind speed here. So it is required to extract the maximum power from the wind, so that the gap between the demand and supply can be reduced. Okay, so mathematically we see the wind power extraction is being totally dependent upon this wind speed, cross-sectional area, and this density here. And further, this mechanical power output is simply, you can see like it is depending upon this mechanical power, directly depend upon this wind power extraction and this CP lambda beta. So in this one, you can see the CP lambda beta, if you see, it is basically like power coefficient here. Okay. So this power coefficient is basically dependent upon lambda and beta. Lambda is called tip to speed ratio and beta is called pitch angle. This is basically a non-linear empirical relationship. So as I have designed this empirical relationship is given by beta 1.5 upon lambda 1.1 plus exponential of lambda 0.2 beta. So once I design this power coefficient here, so I can expect to have this mechanical power here. And that mechanical power is also dependent upon this power coefficient here, because at the end, if you see the maximum power expression is directly dependent upon this power coefficient CP here. So once this power coefficient is maximized, then you can have this more mechanical power output here. So as here you can see this CP, there is a power coefficient depend upon this lambda and beta here. So it can be different, it can be maximized by using our differentiation formula here. Okay. Once the CP is minimized, we can have this more mechanical output here. This is all about the wind sources here. So after doing this, we have this uh, turbine output power variation with the speed. So we can have, see, like more mechanical power, maximum mechanical power is achieved when the wind turbine is, when the one turbine speed is 10 meter per second and a pitch angle of 0 degree here. This is like, again, the maximum power is extracting once when the pitch angle is attained at 0 degree here. Okay. Again, the next solar photovoltaic cell is like the solar PV module here. So in this one, you can see like various modules of solar photovoltaic cells are being connected or cascaded in order to have the more output power here. So in this one, you can see the hourly generated power of PV module is being calculated on the ambient temperature and the solar radiation, because we know that this power generation is directly dependent upon the temperature and solar radiation, and which is mathematically given as there you can see like in this formula here. This PGI dependent upon speed rated power, reference temperature, ambient temperatures, and alpha is called your this coefficient of temperature, SI is called irradiations of incident solar, and SJ is called irradiance of the solar photovoltaic PV array. So this is like that shows the dependency of this output power upon these various input parameters like temperature and all. Because at the end, the solar photovoltaic output is directly dependent on the irradiations, and that irradiations is affecting the temperature and everything here. Next is like another one, we have the BESS. Another type of source is BESS. Last two we have seen the two sources like wind and solar. Another generating source we have the BESS. So this one battery energy storage system you can like. So when the generation of renewable energy sources exceeds the demand, in that case the BESS get charged. BESS can serve purpose both. It can serve both the purpose, load as well as the sources here. Once the renewable energy sources provide the power, the BESS get charged. But when the load demand increases, then BESS in the form of charge can also deliver the power supply to meet the load demand with the help of its discharging. It means that BESS can have both aspects, charging as well as discharging. So this BESS mostly commonly is also used in our electric vehicle system here. Okay. So as here you can see, the mathematically the charging aspect is given by this drive by me. And this is the at any instantaneous point of time, the charging energy is dependent upon this past state as well as its next state. Okay, sorry, past state as well as present state. So as you can see, like t minus 1 minus sigma. So sigma is basically called, you can see like the discharging rate of the battery. Okay, so higher the discharging rate, lesser the charging rate. So that is why I've taken 1 minus sigma. It means we want to have the lesser value of sigma so that we can have more charging. As you can see, this charging is a dependence in the mathematically depending upon both EPV, that is the energy produced by the solar photovoltaic, EWT is the energy produced by your just wind turbine. Okay, so this is the charging aspect by considering both, by considering all the three sources: battery, solar photovoltaic, and wind. Another is to talk about the discharging. Discharging is also dependent. Discharging also work on same part. It also works on the past value and this present value here. And this will also be contributed by this sort of photovoltaic, wind turbine, and all. This is the modeling on general expression of this BESS here. So the next part, our proposed controller, I told you that it is a hybrid hysteresis physiology controller here. This is basically a combination of hysteresis controller and physiology controller here. So design aspect of this hysteresis control scheme and the physiology controller. First, we'll discuss these two separately, then we will integrate these two to have our proposed controller here. Okay. So as you know that the first part is hysteresis controller scheme. So in the hysteresis controller scheme, the actual three-phase current has been compared with our generated reference value, that is IECV. So if you see this diagram here, first we measure our DC voltage and compare with this reference value. After that, the difference of these two is passing to PID controller. Okay. Then the PID controller adjusts the value of Kp, Ki, Kd with the help of our standard method is called Ziegler-Nicholas method here. And at the end, the output of the PID controller has been passed to saturator, which can allow to maintain its limit. And this limit is further being connected with this reference value of this source current, that is three-phase current as ISCBC. Now this current will compare with this measured value. Again, the output of this three-phase current is compared with this generating the error here, and this error is passing to PID controller. And the output of PID controller is basically the gate pulses. And these gate pulses are simply used to give in for driving our converter devices here. So as here you can see, like we have SA, SB, SC. Okay, so these are basically a unit vector for each phase, which is measured by dividing the each phase voltage in the above one. Okay, it is like you can see like VSA upon V equivalent for the SA for the first phase. The second phase is VSB upon VQ, and VSC is called VSC upon V equivalent. And V equivalent is simply like the mathematical like under root of 2 by 3 VSA square plus VSB square plus VG square. If you see it is SA, SB, SC. And this is three-phase output here. And this is allowed to switching the inverter. Our inverter is like a 6 switches. So each phase is going to the 2 switches, one the positive and the next one is for negative one. Same for SB and SC. So this is all about the static control scheme. Next is fuzzy logic controller. Now, same thing, if we check, if we replace the hysteresis controller with the fuzzy logic controller, so we know that the fuzzy logic controller simply converts the crisp value to fuzzy logic value. Okay, so its inputs are in the form of uncertainty, which are being measured in the form of error here. Okay, so we have two types of error here. The first is called error, next one is called change in error. And the rules are being framed. Okay, and the rules are being framed in terms of by using Kremstar rule. That is, if we have to two input like a minimum of a union of B, it means we can have choose either we will select the minimum of A of B. Okay, let's see how. Suppose let us say we have in this one, we have first input is error E. We have taken the 7 membership function. Okay, so all the 7 membership function have assigned a value that we can see. Further, our next input is change in error. For the again 7 membership function, we have this 0.4, 2.5, 2.88, and we have unlike this value. So we apply this operator here. So like if we check E1 E union del E, so it is like 0.5. If we check for the first membership function, let us say x1. The minimum for the x1 is like 0.5 union 0.42. The minimum is 0.42. This is how the particular each value is selected by using this formula here. So as we have seen, the range of this error function is we have taken like 2.9. If error is like in this one 0.023, subsequently for 3 and 4, 3.6. So we have taken the 7 notations for the fuzzy logic. These are the 7 notations, is basically 7 membership functions here. NB, NM, NS, ZS, PS, PM, PV. NB is called negative big, NM is called negative medium, NS is called negative small, ZS is called 0, PS is called positive small, PM is called positive medium, and PV is called positive big. Okay. And their values has been taking like 0.3, 0.6, 3.4, 0.3 and all. Okay. Next, if you see the proposed, if we combine all the previous two, hysteresis and the fuzzy logic controller, so we have this proposed hybrid proposed hysteresis fuzzy logic controller here, proposed fuzzy logic algorithm here. Okay, so our objective function has been developed in the form of hysteresis controller that has been further controlled with the help of this by using fuzzy logic. So then now let's see how this BESS has been trained by using this hysteresis fuzzy logic controller here. Okay, so if we see again, we have measured both charging and discharging energy. These two are compared, and their output goes to PID controller. Again, the output is passed into saturator here, and their values are compared with this reference value. And after that, we having an error. Okay, so that error has been passing through again. I think it's PI controller here. We have taken the two fuzzy logic controller here. First fuzzy logic controller is having our input E2, and next is called E3. And if you see, then again the output of the fuzzy logic controller, first fuzzy logic controller, is going to act as the input for the next fuzzy logic controller. Similarly, the output next input for the second fuzzy logic controller has been taken after the PID controller. Again, the output of the next second fuzzy logic controller is going for the switching pulses of the converter. Okay. So if we see the designing here, so these are the certain, because we have taken the two fuzzy logic controllers, so we have to show designing here. So if we see the first one we have the error and change in error, the input for the first fuzzy logic controller. So we have taken the 7 membership function here, and their values are given on the next table here. like 0.42, 0.54, 0.881, 0.57, and like that. And again, for this second fuzzy logic controller, we have like this Y by even, that is the input for the second fuzzy logic controller. So if you see how you are getting this NB, NM. So as I told you, this membership function has been trained and has been designed by using the Kramster rule. It means the minimum of one input is considered as the final output. Accordingly, this rules has been developed here. So as you can see, the even input is simply the difference between VDC and VDA reference, which is passing to PID controller here. Okay, and the values of this PID controller proportionality constant is like 2.5 for KP, 36.65 for KD, and 57.21 is for KI. Okay. Next is the previously it was the implication of hybrid resistance controller for the BESS. Now next we see for solar photovoltaic inverter how we can apply this one. So again we can see the real power has been the real output power has been compared with this reference value and is passing through PID controller here. And again the output of PID controller has to be defined as particular limit. So that is why saturator is applied here. Thereafter, if we see IABC reference value of this current is measured and compared with this measured value. And the output goes to PID controller here. And this PI controller has been, again, the one output of PI controller is the one of the input of the fuzzy logic controller, and the second input is coming from the comparator. So here you can see like E2 and E3 are the inputs of the fuzzy logic controller here. It is measured here IABC minus IABC star and E3 is for KPK E2 here. And the tuning of this value are being measured with the help of Signal-Nicholas method here. So again, these are in the tabular form. You can see the fuzzy logic rules which are used for the training of this FLC block. Again, this was like a design of the proposed controller. The next one is we have to see the optimal cost of all the individual components. What are the components? Solar photovoltaic, wind energy, and this BESS conventional sources. So we have to measure all these. We have to optimize the overall cost of the system. Okay. So these have been measured in terms of loss of power supply, loss of cost of energy, total harmonic distortion, loss of carbon emission here. So in this one, a multi-objective function has been developed, which includes all the terminologies as we discussed. So let's see it one by one. The first one is called loss of power supply here. It is basically loss of power supply is basically characteristics as a probability of inadequate power supply. So when the hybrid system is unable to meet the load demand, so it is like a probability that how the inadequate power supply can be met. So generally the range of LPSP is like between 0 and 1. So the mathematical expression of this multi-objective function has been developed, like you can see like summation of this the difference between the load and the supply energy, and again the divide by the total load here. As our supply is basically supply energy is contributed to all the sources, wind turbine, this solar photovoltaic discharging and everything. Discharging means it is the power is coming out from the BSS here, because the BSS itself giving a power when it is in the discharging form here. Another aspect is LCOE. Okay, so one of the key goals of this research is we have to minimize this total energy cost, and the total energy cost is basically used for the economic study of a hybrid integrated system, which is like the TR, which is basically the total present cost multiplied by the capital recovery factor and divide by total energy demand. This is the total mathematical expression of loss of cost of energy here. And TPC is the total present cost of the system here. And CRF is the capital recovery factor. And as I told you, and the mathematical, if you see, the CRF is basically like depend upon the rate here, and TPC is depend upon the power rating of each sources like solar, wind turbine, inverter, and charging. Next aspect, as you discussed, if you have an integrated system where a lot of sources are integrated, So they have much more possibility that a lot of harmonics are present. And that harmonics are basically measured in terms of THD. Okay. So if in any system, if harmonics are there, they directly affected our output. It also challenges the power quality issues. Okay. So it is required to minimize the THD level in a permissive range so that we can have a more optimal and smooth output. Okay. That can also be that can also itself is being processed with the help of this proposed controller here. Okay. The next part is the carbon footprint. Now we see the one question arises: why, if we have considered the solar photovoltaic and the wind turbine, as as we have seen the beginning, we have seen they are totally zero. They are providing zero carbon emission solution here. Okay, then what is the need? Then why we are discussing the carbon footprint for these two? That's okay. Basically, practically, we see the solar photovoltaic and wind turbine. They are not providing the carbon footprint, but indirectly, they're also providing the carbon footprint and carbon emission. How? That it is not like to provide the solution in the form of a carbon emission at all. The carbon footprint and the carbon emission is being considered in the form of the indirect form. Then what are the indirect form? Indirect form is like the transportation cost, materialistic cost, thermal losses. These are the indirect form of the carbon footprint of the solar photovoltaic. Same for wind energy. Okay. So as we have seen, the quality of carbon dioxide emitted during the carbon transportation, construction, decomposition phases of PV. So here you can see like the transportations, constructions, upkeep, and decomposition phases of PV. These are the indirect contribution of carbon footprint. Corresponding amount of carbon dioxide released in the air as per includes the extraction, refining, purification of sulfur needed for the installation of solar photovoltaic. Normally, it is seen that the life cycle emission of the monocrystalline photovoltaic is measured around 1392 kilogram carbon dioxide equivalent per kilowatt hour. Okay. It also significantly contribute like 55.3 kilogram carbon dioxide equivalent per kilowatt hour. Okay. That is being considered for the battery here. Again, the energy consumed for the fabrication installation, and if we because we have a lot of components here. This 1392 kilogram is the indirect contribution, indirect carbon foot contribution of the solar photovoltaic. And for this battery energy storage system, we are also contributing the carbon footprint in the form of 55.3 kilogram per kilowatt. And the battery and the inverter are also contributing the energy, this carbon footprint in the form of this 26.3. They are not directly providing. They are just not like they are affecting our environmental. It is not. This is an indirect contribution, indirect carbon footprint contribution from the wind, battery, solar, and all. Okay, in the form of like transportation, materialistic cost, construction, decomposition, which is all. Now we see how we can measure the carbon footprint. The carbon footprint is basically mathematically measured by loss of carbon emission. And this loss of carbon emission, if we see, it is mathematically, we have discussed. One second. Now this we see how we can LCE can be framed out. So the multi-objective function has been framed up. This multi-objective function has been described as a limited non-linear multi-objective process for the different LCOE and LPSP, which are reduced concurrently here and being constrained by the carbon density. So we can see our, as I told you that the carbon footprint are measured in terms of loss of carbon emission, that is LCE. So that LCE has been mathematically derived by me here. It is like one, here you can see like it is depend upon, LCE depends upon rating of solar photovoltaic, wind turbine, inverter, and the charging of both battery here. Okay, so we have seen the indirect contribution of all these renewable energy sources here in the form of carbon emissions. And now the question is where we have taken this direct contribution of this thermal one. So this is being because total power is being developed by the thermal, wind, solar, and all. So this is also being considered over here. So this objective function has been framed under the various constraints that we have to consider the minimum and maximum limit of solar photovoltaic, same for wind turbine, same for inverter, same for battery. Okay, this is how the multi-objective function has been framed. Now we see how this stressless physiology controller has been uh, developed for reducing the carbon footprint. So where certain steps has been developed. So as you discussed, like first we have to check the minimum and maximum range of each generating sources. After the selection of minimum maximum range, what we have to do, we have to select the proportionality constant of PID controller. After this one, we have to set the limit of the saturator here. Then we have to apply the certain physiologic rules for each generating sources here. Now, thereafter, we say the cumulative output from each sources. Then we have to measure the carbon footprint in the form of loss of carbon emissions. So next, see how the carbon footprint can be controlled. It is in the form of LC by using our proposed hybrid hysteresis fuzzy logic controller here. So as here we can see like we have two sources. The first effect is basically like the solar photovoltaic. Next one is the energy contribution here. The another power is from the inverter. Next is from wind turbine. The output of all these four sources are been compared with the reference value, and their output is further passing to PID controller, and the limit set up by this saturator here. And again, it is passing to PI controller so that it can maintain the steady state response here. And again, with the fuzzy logic controller, we have applied to maintain its limit here. Okay. So after that, the output of all the four fuzzy logic controller has been integrated and accumulated. Okay. And that will measure the total carbon emission here, a carbon footprint. That is your LC. Now, after what we see, like after training our multi-objective function with the proposed controller here, we have a certain outputs. We can see like we generally we know that the inverter is totally AC, but here it is a two-level inverter here. So our output is in the form of square waveform because of the harmonics here. It can lie between 765 to -65 here. Similarly, the voltage across non-linear load under the full load condition here, with a proposed controller lying between like this 1, 2, 6. So this should be a pure sinusoidal, but it is like non-sinusoidal here. It is like an impure sinusoidal because of harmonics here. Same thing for voltage across the load, for the quarter load and for half hour load. For quarter load, again, we have seen like the variation, a lot of voltages here, same for voltage because of harmonics. Okay. Now, next one, if we see like, 1 second. Yeah. Now, if we see the comparison of THD under the various loading conditions here. So first we see like for the half load conditions and the full load conditions. So we have checked the compare THD performance with our proposed controller with the existing controller. So we find out for the half loading conditions that THD found to minimum the proposed controller. For the full loading condition, the THD found to be also minimum here. It means our proposed controller works well. So it is providing a lesser THD. It means we are expecting to have a better power quality solutions. It means we can have the more load demands here, more fulfillment of the load demand. Okay. So if the load demand is increasing, it means we can sustainably provide the load demand here. Okay. Next is like if you see, if we compare, because our objective was also like to compare these optimal sizes of the each component here. So if we compare the solar photovoltaic size with the proposed hybrid controller here and the existing technique, so we also find, in addition to power quality solutions, we also find out the rating on the size of this solar photovoltaic cell has also been also reduced. So if you see like for the various value of LPSP, the size of solar photovoltaic cell has been measured. So if you see in compared to the other reference techniques, the size of the LP, the solar photovoltaic, has been reduced a lot. It is found to minimum. Like we compare the one of the article in our reference number 20, it was found to 2.5. But in our study, it is found to 2.1. It means in addition to the power quality, better quality contributions, we are also having a minimal size. Same thing is for wind turbine here. If we same thing, we have also checked for various value of LPSP. The the size of wind turbine, the size of wind turbine is also found to be lesser in comparison to the existing techniques here. So if you find out the size of LPSPA has been reduced a lot. So now next is like after measuring the size of solar and wind, let's check the size of inverter. So again, the dominance of the proposed controller is also works here. If you see like the inverter size has also been reduced. The least size has been obtained with the proposed controller here for the various value of LPSP. It is like 12.65 for the LPSP1, 9.6 for LPSP 2%, 10.35 for LPSP3. Same thing for battery. Our batteries can also reduce when compared to this existing controller. It means like we are getting almost all the optimal solutions with the proposed controller here. That is a better power quality solutions, minimal size of solar photovoltaic, wind turbine, inverter, and battery. And next one is, I think, the most important our result is for which we have designed an LCOE, the loss of carbon energy solutions here. LCOE. So again, we find out the LCO is also find out to be because LCO almost decides the rating or size of the also uh, determine the size of each component. So we find out LCOE also found to be lesser for the various value of LPSP in comparison to the existing technique. So we have taken the reference existing article like reference number 20, 19, and 15. So in comparison to these three articles, our LCOE value is found to be minimum here. That also works well. The last and the most important on which we have worked out is carbon capture. Now let's see how we can minimize the carbon capture, carbon utilization, carbon footprint. As I told you that carbon emission is basically a byproduct produced by the conventional generating units. They simply remark about the emission in the atmosphere in the form of carbon footprint, and these are also being indirectly contributed by our solar photovoltaic, wind turbine, BSS, as I told you, as you have discussed, like in the form of like transportation, decompositions, and all everything. We have also found out the optimal size of this wind turbine, solar, inverter, BSS. In the previous session, we have already seen. Now let's see how we can work on this one. So as I know today, the carbon footprint is basically a difference between the carbon capturing and carbon utilization. So the mathematical expression of carbon utilization as I developed here is like dependency again upon both all the size of all the component like solar photovoltaic, wind turbine, inverter, and charging. And the charging we have considered is maximum minimum limit. Same for inverter, same for wind turbine, same for solar photovoltaic. After designing this, we have measured our carbon emission. LC meaning is called the carbon emission. LC is the mathematical representation of carbon footprint or carbon emission we see. So we find out that the carbon footprint here, it is basically found to be minimum. Okay, it is found to be minimum with our for the various value of LPSP with respect to the convention existing controller. So like here you can see for the first value of LPSP it is 82.66, which is found to be less as compared to the other existing technique like they are providing 86.61, 87.55, 87.99. Same for LPSP 2%, 74.6, lesser as compared to the other one. So it is like the minimum value of carbon emission has been attained for the various value of LPSP in contrast with the existing controller here. Okay. Again, if we check the carbon utilizations with the proposed controller, so again you can see this carbon controller and this carbon utilization is found to be minimum again with the proposed controller and again the proposed controller showing its dominance to obtain this lesser value of carbon utilization in comparison to the existing methods here. That is like we are getting 77.14 for 1% of LPSP, which is found to be lesser in comparison to the existing methods within which we are providing 92.29, 100.25, 111.51. Same for other value of LPSP. Okay. One second. This thing we have already discussed. Now we conclude our full study. So what we have seen, like we know that this conventional generating unit directly provides this carbon footprint and carbon emission that we have considered here. But in addition, in order to minimize this carbon footprint and the and carbon capturing, we have integrated our solar photovoltaic, wind turbine, and BSS as a renewable energy sources in order to have the clean and green energy solutions with reduced carbon footprint and carbon emissions. So we have considered the direct effect of carbon emission produced by the conventional sources and the indirect effect produced by the solar photovoltaic, wind turbine, and the BSS. So it is found to be that all these direct and indirect effect of the carbon footprint has been assessed with the help of a proposed controller. And after implementation of proposed controller, it is observed that the carbon footprint and carbon emission has been reduced a lot. So once the carbon footprint and carbon emission has been reduced in reference with to the existing controller, it means we can say the system is providing a sustainable, clean and green solutions. Okay. So after implicating, we've observed that the average value of our carbon emission is found to be for the various value of LPS is around to 70.64 gram CO2 per kilowatt hour. This is a standard unit. The cost of LC is around 0.5926, which are least among all the methods here. Okay. So this is from my side. Thank you. So if there is any questions from the participants, please let me know.
ये बंदा बोलता है 1 बजे तक
Thank you very much, sir. Thank you, Dr. Shrivastava Saab, Saxena Saab. I think this was one of the very good presentation under which we understood that how this